This is the last section from Chapter 6. 6.3 is the central limit theorem. So statisticians are interested in knowing how an individual data value can vary about the mean for a population. That's what we were looking at so far. What we're going to do in this section is see how the means of samples, so looking at sample means, and these samples come from the same population and they have to be the same size. And we want to know how the means of the samples vary about the mean for a population. So I'm just going to draw a little diagram here, but pause the video if you still need to copy any of this down. So let's just say this box is representing an entire population. Then I'm going to take samples from within this population. They're going to be the same size. I'm going to call this sample 1. They can overlap, sample 2, and even over here, sample 3. But again, samples need to be the same size, come from the same population. We want to see how the means of these samples vary about the mean for a population. All right, so I'm going to define something now called a sampling distribution of sample means. So this is a distribution using the means computed from all possible random samples of a specific size taken from the same population. But the key here is all possible random samples, again, of the same size of a specific size taken from the same population. So let's suppose a researcher selects a sample of 30 adult males and they want to get their mean triglyceride levels for one sample. Let's say that's 187. And then they continue to take samples of the same size and make note of the sample means. So again, let's say that first sample mean was at 187. Then they continue to do this. The next sample mean is 192, and let's say 184, and then they keep doing this. And then the last one would be 196. This is an example of a sampling distribution of sample means. Next, we're going to take a look at something called the sampling error. This is the difference between the sample measure and the corresponding population measure. Because samples are not a perfect representation of a population, they're close enough, but we can get a sampling error. And that's the difference between the sample measure and the corresponding population measure. And this is because samples are not a perfect representation of the population. Again, pause the video if you need to continue writing that down. Next, we're going to take a look at some properties of a distribution of sample means. If all possible samples of size n are taken, then the mean of sample means is equal to the population mean. We're going to write it this way. We're going to say mu of sub x bar here is going to equal mu. So this is just representing the mean of the sample means. Second, the standard deviation, SD, of the sample means will be less than the standard deviation of the population. So this is sigma sub x bar is going to equal the sigma divided by the square root of n, where n is the sample size. And this expression right here, we're going to use this in our new formula now. Sigma over the square root of n, this is the standard error of the mean. Now this third property is actually called the central limit theorem, and it pertains to the shape of the distribution. And what this says, and limit is a key word here, as the sample size n increases without bound, the shape of the distribution of sample means will approach the normal distribution. So as our sample size keeps getting larger and larger, we're going to eventually get the normal distribution shape. So from this, our problems are going to be very similar to what we've been doing before. However, we have a new formula for the z value. It's still going to be x bar minus mu in the numerator, but now we're dividing by the standard error of the mean. Which is sigma divided by the square root of n. This is the standard deviation of sample means. Now the reason we do this, it's adjusted since means are being used instead of individual data values. So now we have to be careful, because if they're mixed together, if we're just given a problem talking about an individual data value, we just use sigma in our denominator. But if it's talking about the mean of sample means, if we're given a sample size, then we use this new formula. And two more things to make note about the central limit theorem. The first is that when the original variable is normally distributed, the distribution of the sample means will be normally distributed for any sample size n. So pretty much this means our problem is going to tell us assume the variable is normally distributed. The second is if the original variable might not be normally distributed, then a sample size of 30 or larger is needed for the sample means to be normally distributed. But overall, the larger the sample, the better the approximation will be. All right, so we're just going to go through 3 examples here using this new formula, or perhaps seeing if we need to use the first formula for an individual or the new version of the formula for sample means. All right, so example one, if you've ever heard of a Nielsen report, that's just like TV ratings, or a company that gets information based on people that watch TV. So AC Nielsen reported that children between the ages of 2 and 5 watch an average of 25 hours of television per week. Assume, here's that one of the things about the central limit there, assume the variable is normally distributed and the standard deviation is 3 hours. So if 20 children between the ages of 2 and 5 are randomly selected, find the probability that the mean number of hours they watch television will be greater than 26.3 hours. So we still go through the same process of what we were doing before. We're going to draw a little sketch of the normal distribution. And we're going to find the z value. So since we're turning this into a standard normal distribution, I'm still going to put 0 here. And then we want to say z is equal, we're going to take the 26.3 minus the 25. But here's what's new. We're going to divide it by sigma, which is the 3. And we're going to divide it by the square root of the sample size, which is 20. And again, we use this new version of the formula because we're given a sample size. So go ahead and calculate this, round again to 2 decimal places. We should be getting 1.94. So we're going to go to mark that right about here. And the question is that we want to see greater than the 26.3 hours. So we're trying to find this area here, which is the probability. So we want the probability that z is greater than 1.94. So go ahead and calculate that. And we should be getting a 0.026. So our answer would be, the probability is 2.6% that the mean number of hours they watch television will be greater than 26.3 hours. All right, a very similar example here. You guys go ahead and pause the video to work this out. And pause the video some more if you need more time. So here we're looking for a probability between. So again, if we mark this at 0, I'm going to go ahead and state that Z1, that's going to be the 90 minus the 96. Over 16. Again, we want to use all of this in months here. 16 divided by the square root of 36. And then Z2 is going to be the 100 minus 96 over 16 divided by the square root of 36. So for this first one, we should be getting a negative 2.25. For the second, a 1.5. So we're looking for this probability right here. So you'd say the probability that z is between negative 2.25 and 1.5. And this should be giving us a 0.921. So we would say about 92.1%. That the mean of their ages is between 90 and 100 months. All right, our third and last example. The average number of pounds of meat that a person consumes per year is 218.4 pounds. Assume the standard deviation is 25 pounds and the distribution is approximately normal. Now I do want to go back and talk about example 2 real quick. I didn't read over this one beforehand, but notice it doesn't say that the distribution is normal, but we do have a sample size of over 30. But here we don't. In fact, in part A, we're not given a sample size. In part B, we are given 40, but that's okay because we're still told that the distribution is approximately normal. So be very careful here. In A, we're just looking at one person, where B, we're looking at a sample of 40 individuals. So pause the video to give that a try. Something I mentioned a little bit ago, we have to note the difference here. All right, so for part A, since we're just looking at an individual data value, we use the former formula. So that would just be Z is going to equal the 224 minus the 218.4, just over 25. Go ahead and write out the formula for part B. The difference here is going to be 224 minus 218.4 divided by 25 over the square root of 40. And again, it's because the sample size is mentioned. All right, so the Z value for part A is going to be 0.22. And then we want the probability that Z is less than 0.22. And we should be getting a 0.587. So good answer here, 58.7% is the probability that a person selected at random consumes less than 224 pounds per year. The Z value for part B, we should be getting a 1.42. So here we want the probability that Z is less than 1.42. And here we should be getting a 0.922. So we would say 92.2% chance that the mean of the sample will be less than 224 pounds per year. So again, we're looking at an individual data value in part A, and we're looking at a sample of size 40. All right, so I will give you guys worksheet 6.3 tomorrow. I want you to, if you still need to finish, but then check the answers to worksheet 6.2, the 11, 16, and 17. I'll show that on the next page here. So 11, these were just the processes for each type of a test for normality. Here's all the data values and the results for number 16. And everything you need for number 17. Please let me know if you have any questions.